Chapter 7 of Power Systems, in which we are going to study different types of AC powers. Now this chapter is basically a revisit to the chapter that you studied in Circuit Analysis or Circuit Analysis 2, where you discussed different types of AC powers. Of course, in power systems, you have the DC power and then you have the AC power. DC power is simply the average value of the power, which you can find using the DC voltage times DC current. AC powers, again, if you remember from circuit analysis, there are 5 different types of AC powers, and those 5 types are written right over here. So you have instantaneous power, that is power at any instant of time, and this is power at any instant of time is simply the product of the voltage, time value, and the current, again function of time. So if you want to find out power at any instant of time through across any component or in any component, all you have to do is to find the voltage, time dependent voltage in that across that component, and the current, time dependent current that is passing through that component. Take the product of those two, put the time value at which you want to evaluate the power, and that will be the instantaneous power at that instant of time. And the unit of instantaneous power is, of course, watt. Active power is the same as DC power. So active power is represented by uppercase P, and active power is also called average power. It is called DC power, and of course active power. And since it is the average power, basically what we do here, we calculate the average of the instantaneous power. Now whenever you're calculating average of any waveform, now remember, voltage is a periodic function of time and current is also a periodic function of time, and of course our voltage and current, they are sinusoidal function of time. So power, instantaneous power, is also a periodic function of time. And when you're finding the average value of any periodic function of time, you can use the formula 1 over 1 period of time, integral over 1 period of time of the function for which you are trying to find the average value, dt. That's basically the universal formula of finding the average value of any periodic function of time. So you calculate area under curve over one cycle of that periodic function of time and divide the whole thing by the time period. It is equivalent to as if you have discrete numbers and you want to find out the average value of those discrete number, you add all the numbers and divide that sum by the total numbers. So if you have 3 numbers, you add all 3 numbers and divide by 3, and that gives you the average value. So it's a similar thing, but it's in the continuous domain. If you have a periodic function of time, you are taking the area under curve, which is adding the area together or adding the function together, and then dividing by the total time period, which is same as dividing that by the total number of element for the discrete counterpart. So we're gonna come back to this a little later in this chapter. Reactive power is represented, and an active power unit is also watt. Reactive power, and one more thing about active power, that it is the power that does some work that you can see. So it's a tangible work or tangible energy that you can see. That's basically active power. It is the power which is it is the power which is dissipated in the resistive part of the circuit only the resistive part of the circuit. So again, we're gonna come back to this. Reactive power is represented by Q, and reactive power is associated with reactive components, that is inductor or capacitor. So the average power that is supplied to an inductor is called the inductive reactive power, or simply reactive power of inductor, and average power that is given up by capacitor. On average, capacitor over one cycle, it gives up the reactive power. So that's the reactive power, is the power that is associated with capacitor, and capacitor reactive power is negative, as you will see shortly why, and inductor reactive power is positive. So anytime you have bunch of reactive powers given to you and you have to add all of them together, make sure put a negative sign for the capacitive reactive power and the positive sign for the inductive reactive power, and then add them together to find the total reactive power of that system. So reactive power is the unit of that is volt ampere reactive, VAR. Okay, complex power. Complex power is basically represented by S, and it is simply P plus JQ. That is the active power plus JQ, reactive power. And Q, as I said, can be negative or positive. Negative for if your total reactive load is capacitive, Q will be negative, so it's going to become P minus JQ in that case. And if total reactive load is inductive, Q will be positive, so it's going to be P plus JQ in that case. So that's your complex power, and the unit of complex power is volt ampere, simply volt ampere. And apparent power is simply the magnitude of complex power. So apparent power is the magnitude of complex power. Since it's a complex number, you have a magnitude as well as phase. So the magnitude of complex power is the apparent power, which is P square plus Q square, and which can also be calculated as the magnitude of the voltage and magnitude of the current. And the unit again is volt ampere, voltage times current. So let's go and look at each of these power in a little more detail. So we discussed instantaneous power. If your voltage signal is a cosine signal, Vp cosine omega t plus theta, current signal is Ip cosine omega t plus phi. Of course, Vp and Ip are the peak value, theta and phi are the respective phase angles. And then instantaneous power is the product of these two, as you can see. So you multiply both of these together, you're gonna get this. And then when you are, in general, when you're analyzing this type of function, when you have cosine A, cosine B, generally you divide that, as you will see shortly actually. Cosine A, cosine B is using trigonometric identities, is cosine A plus B plus cosine A minus B divided by 2, as you will see shortly actually. I think I'm driving it for the active power. Now time domain signal, sinusoidal time domain signal, of course, when we are solving the sinusoidal circuits, the AC circuit at a steady state, if you remember from circuit analysis, we convert everything into phasor domain, right? So Vt cosine omega t theta in the phasor domain is represented by a complex number in polar form, magnitude of the time domain cosine signal, and the phase of the time domain cosine signal. So we suppress cosine, we suppress omega t, and we represent that by Vp angle theta. And likewise, the phasor quantity of the current is represented by Ip angle phi, because the corresponding time domain signal was Ip cosine omega t plus phi. So again, this is from circuit analysis. The impedance of your circuit is the ratio between voltage and current. So Vj omega over Ij omega. Now Vj omega is Vp angle theta, Ip angle phi, and whenever you have a complex number written in a fractional form and each complex number is given in polar form, then of course the result of that is going to be the magnitude of that is going to be the magnitude Vp over Ip, and the phase is angle of the numerator minus angle of the denominator, so theta minus phi. So this is your magnitude, and this theta minus phi is basically the angle of the impedance. As you will see, this theta minus phi will have an utmost importance in the power systems, because this is the angle that is associated with the power factor, as we will discuss shortly. So second type of power is active power. As I discussed earlier, active power is also called real power, average power, DC power. All of the names are for active power. Unit is watt, and active power, as I mentioned, is the average value of instantaneous power. So right here, this is what I explained earlier. Active power is calculated as 1 over time period and the area under curve over 1 time period of the instantaneous power signal. So once you expand it, basically you put PT, Vp, Ip, cosine omega t theta, omega t phi, and then as I showed you earlier, we split cosine omega t theta, cosine omega t phi into two functions using cosine A plus B plus cosine A minus B divided by 2. And once you take the integral of that, then you are going to get Vp Ip over 2 cosine theta minus Py, because this integral can be broken down into two pieces from 0 to 2 pi. And observe, from the time domain I moved into the radians, that is the angle d omega t, because it's just easier to solve it. Of course, area under curve is going to be same, either you are in the time domain or you are in the angle domain. So cosine 2 omega t plus theta plus phi d omega t, and then plus cosine theta minus phi d omega t. Right, so we split this function into two, we take this 2 out. So this function over one cycle will have basically two cycles over one time period, because the frequency is double the amount of the original frequency, right? So in one time period, this is going to periodically, this is going to change 2 times. Now remember, this is area under curve, and if you have a cosine function or sine function, I'm showing sine but it's the same thing. If you have cosine or sine function over one cycle complete signal, or over 2 cycle, or over 3 cycle, the positive area will always be equal to negative area and they will cancel each other. So that's why I did not even bother to evaluate this over one cycle, because I know the area is going to be 0. Now if you want to do it, make sure you do it, but you will see area is 0. It just makes sense, right? Now if this would be 1.5 cycle, then of course the area would not be 0, and then of course you will have to evaluate it to find the total area. But all the complete cycles, if you add them over one time period or 2 time period, they will always give you 0 area. So this is basically gonna turn out to be 0, and the only thing will be left is this. Of course this is a constant number, so we pull that out, and then we take the integral of 1/2 from 0 to 2 pi. That's gonna give you 2 pi. 2 will be cancelled out, pi will be left, and pi, and this pi is gonna be cancelled out. That's why you see it's Vp Ip over 2 cosine theta minus phi. Now again, if you're confused, you can drive it. It's very easy to drive this function, right? I'm not showing you a couple of steps here, but drive it, it's very easy. Okay, so Vp I'm writing down as Vp over square root of 2. Ip I'm writing down, Vp Ip over 2 I'm writing as Vp over square root of 2, and Ip over square root of 2, which is the same thing, cosine theta minus phi. Now why I'm writing down like this? Because we know that for cosine or sine sinusoidal signal, the RMS value of sinusoidal signal is the peak value over square root of 2. Now this is for sinusoidal signal, remember. RMS value is different for different types of signals. For sinusoidal signal, if you take the root mean square, that is you square the signal, you average the signal, that is take the mean, and then you take the square root of the signal. It is going to give you peak value over square root of 2. That's how you calculate root mean square of any periodic signal. You first square the signal. So for example, if you have x of t is equal to sine omega t, right? So first you're gonna square the signal, x square t, which will be equal to sine square omega t. And then let's say V peak is here as well. So V peak sine omega t, V peak is square. And then you're going to take the average value of this. And remember, we just discussed if you're taking the average value of any periodic signal, that's basically 1 over time period, 0 or to complete time period, x square t dt. And then you take the square root of that. So this is going to be the RMS value of x, and that's how you find the RMS value of any periodic signal. You first square the signal, then take the average or mean, and then you take the square root of that. So once you do that for Vp square sine square omega t, this is you're gonna get Vp over square root of 2. So that's why Vp over square root of 2 is the RMS value of the sinusoidal signal. So that's why you see here that the average power is equal to RMS value of the voltage times the RMS value of the current cosine theta minus v. And this cosine theta minus v, as you will see soon, this is called the power